Welcome! Today, we'll explore an exciting problem, number 1482, minimum number of days to make bouquets. We'll break it down step by step, understand the intuition, and discuss the approaches to solve it effectively. Let's dive in. In this problem, we are tasked with determining the minimum number of days required to create a specific number of bouquets from a garden of flowers. Each flower in the garden takes a certain number of days to bloom, as indicated by the bloom day array. For example, if bloom day I equals 3, it means that ith flower will bloom on the third day. You are also given two additional parameters, m, which represents the number of bouquets you need to create, and k, which specifies the number of adjacent flowers required to form one bouquet. The key point is that all the flowers used to create a bouquet must have bloomed by the same day. If it is not possible to create the required number of bouquets, the function should return -1. This is the essence of the problem, to calculate the minimum number of days needed, or determine if it's impossible. Let's look at a practical example to understand the problem better. Suppose the bloom day array is 1, 10, 3, 10, 2, and you need to make m equals 3 bouquets, where each bouquet requires k equals 1 flower. Here, since each bouquet only needs 1 flower, we can pick any flower that has bloomed by a given day. On day 1, only the first flower blooms, so we can make just 1 bouquet. By day 2, the 5th flower also blooms, allowing us to make 2 bouquets. Finally, on day 3, the 3rd flower blooms, which lets us create the 3rd bouquet. Thus, by day 3, we have enough flowers to make all 3 bouquets, and the answer is 3. This demonstrates how the blooming schedule and the values of m and k interact to determine the result. Now consider a slightly different example with the same bloom day array, 1, 10, 3, 10, 2, but this time we need m equals 3 bouquets, where each bouquet requires k equals 2 adjacent flowers. This introduces a new challenge, as we need pairs of flowers that are next to each other and have bloomed by the same day. Looking at the array, we can see that it is impossible to find 3 such pairs. Even on the last day, there are not enough adjacent flowers to meet the requirement. Since it is impossible to create the required bouquets, the function should return -1. This illustrates how the adjacency constraint can limit the ability to form bouquets, making it crucial to carefully evaluate the conditions. Finally, let's explore another example where the bloom day array is 7, 7, 7, 7, 12, 7, 7, and the requirements are m equals 2 bouquets, each requiring k equals 3 adjacent flowers. On day 7, the first 4 flowers bloom. This allows us to create 1 bouquet using the first 3 flowers, but we still need another bouquet. By day 12, all the flowers in the garden have bloomed, and we can use the last 3 flowers to create the second bouquet. Therefore, the minimum number of days required to meet the bouquet requirements is 12. This example highlights how the solution must account for both the blooming schedule and the adjacency requirement to determine the earliest day when all conditions are satisfied. Lastly, keep in mind important constraints such as the size of the input in edge cases, like when there aren't enough flowers or when all flowers bloom simultaneously. To solve this problem, we first considered 2 approaches. The brute force approach is straightforward but inefficient. The idea here is to check every possible number of days, from 1 to the maximum value in the bloom day array, and determine if we can create the required number of bouquets within that time frame. For each day, we iterate through the array, grouping flowers that have bloomed together to form bouquets. While simple to implement, this approach is computationally expensive because it involves iterating through the bloom day array for every possible day. The time complexity, O, max, bloom day, multiplied by n, where n is the length of the array, makes this approach impractical for larger inputs. Recognizing these drawbacks, we turn to an optimized solution using binary search. This approach takes advantage of the problem's monotonic property. If it's possible to form the required bouquets in a given number of days, it will also be possible in any greater number of days. This key observation allows us to narrow down the search space efficiently. Instead of incrementally checking each day, we search over a range of days using binary search. This involves defining a decision function to determine if we can make the bouquets within a given day count. Now, let's understand the binary search approach in more detail. The time complexity of this method is O, n times log of max bloom day. Here, we perform a binary search over the range of possible days, and for each midpoint, we iterate through the Bloomday array to check if the condition is satisfied. This is a significant improvement over the brute force method because the search space is reduced logarithmically. The advantages of this approach are clear: it scales well for large inputs and avoids the inefficiencies of the brute force method. Binary search is the chosen strategy because it efficiently narrows down the minimum number of days required by leveraging the monotonic property of the problem. While it may be slightly more complex to implement than brute force, the added complexity is manageable and is offset by the substantial performance gains. To further highlight the benefits, the helper function used in this approach is straightforward. It simply iterates through the Bloomday array and counts the bouquets that can be formed within the given day count. The breakthrough moment here is the realization that we don't need to iterate through all possible days. By focusing on the decision function, we can efficiently pinpoint the minimum day using binary search. In conclusion, the binary search approach is the ideal solution for this problem. It balances efficiency and clarity, making it both effective and practical. Unlike the brute force method, it avoids unnecessary computations and solves the problem in a reasonable timeframe, even for larger inputs. By leveraging the monotonic property of the problem, this approach ensures that we can handle cases with large values of n and Bloomday seamlessly. The strategy's efficiency, combined with its logical implementation, makes it the preferred choice for tackling this challenge. To solve the problem of finding the minimum number of days required to form exactly m bouquets, we start by understanding the constraints and requirements. Each flower blooms on a specific day, defined by the Bloomday array. To create a bouquet, we need k adjacent flowers that have bloomed. The objective is to determine the minimum number of days needed for this, or return -1 if it's not possible to form m bouquets. One important constraint is that if m*k exceeds the number of flowers n, it's immediately impossible to create the required bouquets since there aren't enough flowers available. A brute force approach, where we evaluate every possible day and count valid bouquets, would be computationally expensive, especially for large inputs. Therefore, we need a more efficient strategy. This is where binary search comes in as a powerful optimization tool, leveraging key properties of the problem to reduce the computational complexity. The key insight that makes this problem suitable for binary search is the monotonicity of the feasibility function. If it is possible to form m bouquets in x days, it will also be possible to do so in any number of days greater than x. Using this property, we can define the range for our binary search. The minimum value, left, is the earliest day any flower blooms, which is the smallest value in Bloomday. The maximum value, right, is the latest day a flower blooms, or the largest value in the array. To determine feasibility for a given day mid, we traverse the Bloomday array, counting consecutive bloomed flowers. If we find k consecutive flowers, we increment the bouquet count. If the bouquet count reaches m, then it's feasible to form m bouquets in mid-days. Otherwise, we continue checking. By iteratively adjusting the binary search bounds based on feasibility, we efficiently narrow down the minimum day required. The result of our binary search is the smallest feasible day mid where it is possible to form m bouquets. If no such day exists, we return -1 to indicate that it's impossible to meet the requirements. Key insights that make this approach efficient include the monotonic nature of the feasibility function, which allows binary search to work, and early pruning of invalid cases. For example, if m*k exceeds n, we immediately return -1 without further computation since there aren't enough flowers. The time complexity of this solution is determined by the binary search and the feasibility check. Binary search operates in O, log, max, Bloomday iterations, while each feasibility check involves a single pass through the Bloomday array, which is O, n. Therefore, the total complexity is O, n log, max, Bloomday. By combining this with simple data structures like counters and a linear array traversal, we achieve an efficient solution that handles large inputs gracefully. To handle various edge cases, we ensure robustness in our algorithm. For example, if there aren't enough flowers to form the required bouquets, we terminate early. If all flowers bloom on the same day, the binary search quickly identifies that day as the result. For scenarios where no bouquets can be formed, the algorithm ensures that -1 is returned. When working with large arrays or values in Bloomday, binary search ensures efficiency by drastically reducing the number of days we need to evaluate. The pseudocode for this solution begins with a helper function, canMakeBouquets, which checks if it's feasible to form m bouquets in a given number of days. It iterates through bloom day while tracking consecutive bloomed flowers and counting bouquets. The binary search logic adjusts the range based on the feasibility result, narrowing down until the minimum day is found or confirming no solution exists. This structured approach ensures both clarity and performance. The final step in the algorithm is to return the result of the binary search. If the left boundary of the search range satisfies the feasibility condition, it represents the minimum number of days required to form the bouquets. Otherwise, we return -1, indicating that it's impossible to meet the requirements. Let's go through an example. Given bloom day equals 1, 10, 3, 10, 2, m equals 3, and k equals 1, we start with the range left equals 1 and right equals 10. In the first iteration, we check the midpoint, day 5, and find that only 2 bouquets can be formed, so we shift the range. In subsequent iterations, we refine the range until day 6 is identified as the minimum day where 3 bouquets can be formed. The algorithm efficiently handles this by reducing unnecessary checks, and the final output is 6 days. This example demonstrates how the binary search and feasibility function work together to solve the problem optimally. In this implementation, we start by defining a class called solution and a method named mindays within it. This method takes 3 parameters: bloom day, which is the list of integers representing the days on which flowers bloom, m, the number of bouquets we need, and k, the number of flowers required per bouquet. First, we perform a quick check to see if it's even feasible to make the required number of bouquets, based on the total number of flowers available. If m multiplied by k exceeds the length of bloom day, we return -1 because it's impossible to meet the requirement. Next, we define a helper function called canMakeBouquets, which will check if we can create the required number of bouquets within a given number of days. Inside this function, we initialize counters for bouquets and flowers. Then, we iterate over each bloom day in the bloom day list. If the bloom day is less than or equal to the given number of days, we increment the flowers counter. Once the flowers counter reaches k, we increment the bouquets counter and reset the flowers counter to 0, since we've just formed a bouquet. If the bloom day exceeds the allowed days, we reset the flowers counter to 0. To optimize the process, we return true as soon as the bouquets counter meets or exceeds m, otherwise, we return false after the loop finishes. Finally, we set up a binary search by initializing the left and right pointers to the minimum and maximum values in the bloom day list, respectively. The variable answer is initialized to -1, which will store our final result. Here, we implement the binary search loop to find the minimum number of days needed. While the left pointer is less than or equal to the right pointer, we calculate the midpoint by averaging the left and right pointers. We then check if it's possible to make the required number of bouquets within mid-days by calling the canMakeBouquets function. If the function returns true, it means it's feasible to achieve the goal within mid-days, so we update the answer to mid and adjust the right pointer to mid-1, to continue searching for potentially smaller values. Otherwise, if canMakeBouquets returns false, it means mid-days is insufficient, so we adjust the left pointer to mid+1 to search for larger values. Once the binary search completes, we return the answer, which now holds the minimum number of days required to make m bouquets. If no valid number of days was found during the binary search, the answer will remain -1, which correctly reflects that it's impossible to meet the requirement. Here, we start by defining the mindays method, which takes an array bloom day, the number of bouquets m, and the number of flowers per bouquet k. The first thing we check is whether it's even possible to create m bouquets given the total number of flowers. If the total number of flowers, which is the length of the bloom day array, is less than m*k, we can immediately return -1, as it's not feasible to meet the requirement. Next, we define a helper function canMakeBouquets that determines whether it's possible to create m bouquets within a given number of days, represented by the variable days. Inside this function, we iterate through the bloom day array. If a flower's bloom day is less than or equal to the current days, we count it as a usable flower. Once we gather enough flowers to complete one bouquet, we increment the bouquet counter and reset the flower counter. However, if we encounter a day where the bloom time exceeds the current days, we reset the flower count to 0. If at any point the number of bouquets meets or exceeds m, the function returns true, indicating that it is possible to make the required bouquets within these days. If the loop completes without meeting the required number of bouquets, the helper function will return false. Now, to find the minimum number of days needed, we use binary search. We initialize left to the smallest bloom day in the array and right to the largest bloom day using arrays.stream to calculate the minimum and maximum values. The variable answer is initialized to -1 to store the potential result. While left is less than or equal to right, we calculate the middle value mid as the average of left and right. If the canMakeBouquets function returns true for this mid value, it means we can satisfy the condition within mid days. In that case, we update answer to mid and narrow our search by setting right to mid 1. On the other hand, if canMakeBouquets returns false, we adjust the search range by setting left to mid +1. This process continues until the binary search completes, at which point we return the answer, representing the minimum number of days required to make M bouquets. The problem requires us to determine the minimum number of days needed to create M bouquets, where each bouquet consists of K flowers. A flower is available for picking only if its bloom day is less than or equal to the current day we are considering. If it's not possible to create the required bouquets, the function should return -1. For example, with the bloom days 1, 10, 3, 10, 2, M equals 3, and K equals 1, we need a total of M * K is equal to 3 times 1 equals 3 flowers to form the bouquets. Since there are 5 flowers available, which is greater than or equal to the required 3, it's feasible to try solving this. To efficiently find the solution, we initialize binary search. The search range is set between the minimum bloom day, which is 1, and the maximum bloom day, which is 10. Initially, the answer is set to -1, indicating that no solution has been found yet. We now perform binary search to find the minimum number of days. In the first iteration, the midpoint of the range is calculated as 1 + 10 / 2 equals 5. To check if bouquets can be made in 5 days, we traverse the bloom days and find that flowers with bloom days 1, 3, 2 can be picked, allowing us to form 3 bouquets. Since this meets the requirement of 3 bouquets, we update the potential answer to 5 and narrow the search range by setting right to 4. In the second iteration, the new midpoint is 1 + 4 / 2 equals 2. Checking for 2 days, only flowers 1, 2 are available, which allows the formation of just 2 bouquets. This is insufficient, so we increase the range by setting left to 3. In the third iteration, the midpoint is 3 + 4 / 2 equals 3. Flowers 1, 3, 2 can once again form 3 bouquets, meeting the requirement. The answer is updated to 3, and right is set to 2. At this point, the search ends, and the minimum number of days required is determined to be 3. In another example, we consider the bloom days 7, 7, 7, 7, 12, with M equals 2 and K equals 3. The total flowers required here are M * K is equal to 2 times 3 equals 6. However, only 5 flowers are available, which is fewer than the required 6. This makes it impossible to form the desired bouquets, so we immediately return -1. In a different scenario, let's examine the bloom days 1, 10, 3, 10, 2, with M equals 2 and K equals 2. Here, the total flowers required are 2 * 2 equals 4, while 5 flowers are available, making it feasible to proceed. We initialize binary search with the range left equals 1 and right equals 10, and the answer is set to -1 initially. Continuing with the binary search for M equals 2 and K equals 2, the first midpoint is calculated as 1 + 10 / 2 equals 5. Checking for 5 days, flowers 1, 3, 2 are available, but they only form 1 bouquet of size 2, which is insufficient. So, we increase left to 6. In the next iteration, the midpoint becomes 6 + 10 / 2 equals 8. Again, only flowers 1, 3, 2 form 1 bouquet, so we update left to 9. The midpoint for the third iteration is 9 + 10 / 2 equals 9. The same flowers form just 1 bouquet, so left is updated to 10. Finally, for mid equals 10, all flowers 1, 10, 3, 10, 2 can be used to form 2 bouquets, meeting the requirement. The answer is updated to 10, and the search ends. Thus, the minimum number of days required to make the bouquets is 10. To analyze the time complexity of our solution, we start with the binary search component. The binary search operates over a range of days, which spans from the minimum bloom day to the maximum bloom day in the bloom day array. If we let n represent the size of the array and r represent the range of days, which is max, bloom day, min, bloom day, the binary search will have this range in each iteration. This means the number of iterations is proportional to log r. Within each binary search iteration, we call the canMakeBouquets function to check whether it's feasible to make the required number of bouquets within a certain number of days. This function iterates through the bloom day array in linear time, contributing a complexity of O, n, per call. Combining these two components, the binary search runs for O, log, r, iterations, with each iteration requiring O, n, time for the canMakeBouquets function. Therefore, the overall time complexity of the solution is O, n asterisk log, r. Now, let's look at the space complexity. The solution uses constant space because no additional data structures are required. Specifically, the canMakeBouquets function uses only two integer variables, bouquets and flowers, to track the current state. Similarly, the binary search itself only requires variables to store the search bounds, namely left, right, mid, and the final answer, answer. Since all of these use fixed memory, the space complexity is O(1). When analyzing the best, average, and worst cases, we find that the time complexity remains O, n asterisk log, r, in all scenarios. In the best-case scenario, the minimum day that satisfies the condition is found in the first or early iterations of the binary search. However, the binary search structure remains unchanged, and the canMakeBouquets function is still called in each iteration. The same reasoning applies to the average and worst cases, where the binary search continues logarithmically until the search range is exhausted. Thus, the time complexity stays consistent across all cases. When we compare this optimized approach to a brute force solution, the efficiency gains become clear. A naive solution would involve checking every possible day in the range from min, bloom day, to max, bloom day. For each day, we would need to iterate through the bloom day array to determine if it's possible to create the required number of bouquets. This results in a time complexity of O, r asterisk n, whereas the range of days in n is the size of the array. In contrast, the optimized solution replaces the linear search over days with a binary search, reducing the dependency on r from O, r, to O, log, r. Since logarithmic growth is much slower than linear growth, this optimization is particularly impactful for large inputs. Mathematically, the binary search ensures that the search space is halved in each iteration, leading to O, log, r, steps. Each step involves a linear scan of the bloom day array, contributing O, n. Combining these, the overall time complexity becomes O, n asterisk log, r, making the optimized approach far more efficient. In summary, the solution effectively tackles the problem by leveraging binary search to minimize the search space, significantly improving upon the brute force approach. By reducing the dependency on the range of days or from linear O, r, to logarithmic O, log, r, and maintaining constant space complexity, the algorithm achieves both time and memory efficiency. These optimizations are particularly valuable for handling large input sizes, making the solution both practical and scalable. This section highlights some common mistakes to avoid when solving this problem. First, there's a misunderstanding about where binary search is applicable. Many assume it only works on sorted arrays, but that's not the case. Binary search is perfectly suited for monotonic functions, meaning functions that are either entirely increasing or decreasing. In this problem, the number of days needed to make the bouquets is a monotonic function, which makes binary search an ideal approach. Another error is related to the midpoint calculation. If you use the formula low plus high /2, it can lead to integer overflow in some programming languages. Instead, always use the safer alternative, low plus high low /2. A third frequent issue is failing to reset the bouquet count after forming one. Remember, bouquets are formed sequentially, and any extra flowers left over after forming a bouquet cannot be reused. Always reset your count properly after each bouquet is made to ensure accurate results. Another common pitfall is inefficiency when using a brute force approach. A naive solution iterates through all possible days and checks for bouquet formation, but this leads to a prohibitive time complexity of O, max, bloom day, *n. For larger inputs, this becomes computationally expensive. By using binary search, we can significantly optimize this to O, n *, max, bloom day. Additionally, it's critical to manage edge cases. For instance, if the total number of flowers required to make M bouquets exceeds the available flowers, that is, if M*K len, bloom day, it is clearly impossible to meet the requirement. Always check this condition at the start to avoid unnecessary computation. Now let's discuss some interview insights that can help you approach this problem with confidence. Recognizing patterns is key. Many problems that ask for a minimum number or have constraints like maximum capacity can benefit from binary search on the answer space. Identifying this pattern early can save valuable time. Additionally, it's important to clarify the problem requirements. For example, ensure you fully understand what minimum days required or exact number of bouquets means in the context of the problem. Misunderstandings here can lead to incorrect solutions. Be prepared for edge cases, such as when the bloom day array contains all identical values, when M*K exceeds the number of flowers, or when the array is very small. Finally, be ready to explain your optimization choices. Transitioning from a brute force solution to binary search isn't just about reducing time complexity, it's also about demonstrating a deeper understanding of algorithm design. It can also be helpful to explore related problems that use a similar approach. For instance, LeetCode problems like split array largest sum, cocoa eating bananas, and capacity to ship packages within D-days all involve binary search on the answer space. These problems, like the current one, require you to determine a minimum or maximum value under certain constraints. When it comes to alternative approaches, brute force is the simplest to implement. You can test each day from 1 to the maximum bloom day, checking whether enough bouquets can be formed. While straightforward, this method is computationally expensive with a time complexity of O, max, bloom day, *n. On the other hand, binary search on the days range is much more efficient. By narrowing the search space using the monotonic property, you reduce the complexity to O, and *log, max, bloom day. However, binary search requires a strong understanding of how to apply it to monotonic functions. Finally, let's briefly touch on the two-pointer simulation method as another alternative. Here, you use 2 pointers to track bouquet formation in a single pass through the array. This method can be efficient in certain variations of the problem, especially when the constraints are less dynamic. However, it lacks the generality of binary search, particularly when the day constraint changes or becomes more complex. While it's a useful technique in some scenarios, binary search remains the more robust and scalable approach for solving this problem efficiently. Great job following along. To recap, we learned how to approach the problem strategically and apply an efficient solution. Remember, concepts like binary search are crucial for competitive programming and interviews. Thanks for watching, and see you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!